An elastic modulus, or modulus of elasticity, is a number that measures an object or substance's resistance to being deformed elastically when a force is applied to it. The elastic modulus of an object is defined as the slope of its stress/strain curve in the elastic deformation region. A stiffer material will have a higher elastic modulus. An elastic modulus has the form where stress is the force causing the deformation divided by the area to which the force is applied and strain is the ratio of the change in some length parameter caused by the deformation to the original value of the length parameter. If stress is measured in pascals, then since strain is a dimensionless quantity, the units of I will be pascals as well. Since the strain equals unity for an object whose length has doubled, the elastic modulus equals the stress induced in the material by a doubling of length. While this scenario is not generally realistic because most materials will fail before reaching it, it gives heuristic guidance, because small fractions of the defining load will operate in exactly the same ratio. Thus, for steel with a Young's modulus of 30 million psi, a 30,000 psi load will elongate a 1-inch bar by 1,000th of an inch. Similarly, for metric units, a load of 1,000th of the modulus will change the length of a 1 meter rod by a millimeter. Specifying how stress and strain are to be measured, including directions, allows for many types of elastic moduli to be defined. The three primary ones are: Young's modulus describes tensile elasticity, or the tendency of an object to deform along an axis when opposing forces are applied along that axis. It is defined as the ratio of tensile stress to tensile strain. It is often referred to simply as the elastic modulus. The shear modulus or modulus of rigidity describes an object's tendency to shear when acted upon by opposing forces. It is defined as shear stress over shear strain. The shear modulus is part of the derivation of viscosity. The bulk modulus describes volumetric elasticity, or the tendency of an object to deform in all directions when uniformly loaded in all directions. It is defined as volumetric stress over volumetric strain, and is the inverse of compressibility. The bulk modulus is an extension of Young's modulus to 3 dimensions. 3 other elastic moduli are axial modulus, Lama copyright S first parameter, and P-wave modulus. Homogeneous and isotropic materials have their elastic properties fully described by 2 elastic moduli, and one may choose any pair. Given a pair of elastic moduli, all other elastic moduli can be calculated according to formulas in the table below at the end of page. Inviscid fluids are special in that they cannot support shear stress, meaning that the shear modulus is always 0. This also implies that Young's modulus is always 0. See also: bending stiffness, dynamic modulus, elastic limit, elastic wave, flexural modulus, Hooke's law, impulse excitation technique, proportional limit, stiffness, tensile strength, transverse isotropy. References. Further reading: Hartsuiger, C. Wellman, J. W. Engineering Mechanics. Volume 2. Springer. ISBN A978-1-4020-4123-5A.